All right, so last segment, we're going to look at the ideal Zener diode model. So this is going to be very similar to the knee voltage model that we looked at for normal silicon rectifier diodes. And we're going to see that the reverse breakdown line is almost vertical, which is what we saw here before, and just using our graph where we had looking at different tempcos for Zener and avalanche diodes. And that means we're going to have that near constant voltage independent of the current that's flowing through the diode. So a little bit different terminology for the same general idea. Our breakdown voltage is indicated VZ because we're looking at Zener diodes. And that's going to be very similar idea to our VK, which is the knee voltage. And then our current is just going to be indicated IZ to indicate the breakdown voltage for our Zener diode. Okay, so this is our ideal Zener diode model right here. And we see that we have the diode hooked up in reverse bias. So we've got the arrow flowing the opposite, or pointing the opposite direction that we would expect current to flow through the circuit. And this is actually going to flow in that direction against the diode arrow. And that's going to be okay because this is designed for that. And we can tell the difference between that and a normal diode, because this would be our normal diode with the straight bar across, but our Zener diode has this kind of Z-shaped bar across. So that's telling us it's a Zener diode, and that's fine for it to be hooked up in reverse bias, and that's where it's actually designed to operate. Okay, so we have a 9-volt source right here, and we have a 300 ohm resistor. We have the Zener diode. This is a part number for a Zener diode. And this right here is the breakdown voltage for this particular Zener diode. And in order to know if current is going to flow, we need to see if our voltage source is greater than our Zener diode breakdown voltage. So that's what we're looking at right here. First, we see if it's in reverse bias because that's where we want a Zener diode to be in order to have current to flow. And then we need to see if that voltage source is greater than the breakdown voltage. And this is 9 volts, which is obviously greater than 3 volts. So yes, and we're going to have current flow through this circuit. So then we do exactly what we did with the knee voltage model, which is replace this diode with a voltage source that is equal to the knee voltage, or in this case, the breakdown voltage for that particular diode. So this is replaced with a 3-volt voltage source. And then we're going to have this equation right here, which gives the current flowing through the diode. And it's going to be the current that's also flowing through this resistor and flowing through this voltage source since everything is in series. Okay, so we know that the voltage is going to be 3 volts. That's our VZ, because it's fixed at 3 volts since we have sufficient voltage applied to put this in reverse bias. So we're going to be, if we draw our graph, we're in the reverse bias region. And right here is where our breakdown voltage happens. So this is VZ. And we're interested in what the current is. So just like before, we find this current by finding the current that's actually flowing through this resistor. And that would be the voltage across that resistor divided by the value of the resistor. And that's what we have right here. And how this voltage is found is through Kirchhoff's voltage law. So we take Vs is equal to the drops in the circuit, which would be VR1 plus Vz. This value is given, this value is given, so we just rearrange this to say VR1 is equal to Vs minus Vz. We know what these are, which means we can now find VR1. So this gets placed right here, and we're still dividing by R1. So this is how we get our equation for finding the Zener diode current. Okay, so that's reverse bias for a Zener diode, when we have a sufficient voltage to actually put the Zener diode in breakdown. And then we have this other case, which is reverse bias. And this is when the voltage source is not sufficient to put that Zener in breakdown. So this is now a 1.5 volt source, but we still have the same diode, which has a 3 volt breakdown voltage. So looking at our graph again, we're in the breakdown region, but now instead of being in this area, we are in this area right here. So this is applying a voltage that is not quite sufficient to actually have that diode break down. So when that happens, this is going to have no current flowing through it. Remember, this is voltage on the horizontal axis, this is current on the vertical axis. So we have some voltage that is being applied across, but we have zero current. So since we have zero current, that means we model this as an open switch. So it's open, we can't have any current flow because the circuit is no longer complete. But since we have an open circuit, whatever voltage is applied is what's going to be dropped across that diode, which is acting like an open. So VZ is equal to the source voltage, which in this case is 1.5 volts. And then finding the current is easy because it's acting like an open. It's going to be 0 amps. Okay, so we'll do an example. So for this example, we're looking at a reverse biased Zener diode, and it's hooked up in the same configuration that we were just looking at. So we have a voltage source that is 9 volts because we're looking at the same circuit that we had before, and that circuit had a resistor equal to 300 ohms. This is hooked up to our Zener diode, which is in reverse bias and has a breakdown voltage of 3 volts. You can indicate that with VB for breakdown or VZ since it's the Zener diode voltage. Okay, so that's across here. And looking at our current formula, we know that I is going to be equal to VS minus VZ, and that's divided by the value of the resistor. So we just have to plug in values. We get 9 volts minus 3 volts, because 9 volts is our value of Vs, 3 volts is our value of the Zener breakdown voltage, and we divide by 300 ohms. So this is going to be 6 volts divided by 300 ohms, and that's going to give you 0.02 amps. And then if we want to translate that to milliamps, we just take this decimal point, move it 3 places over to the right, and that would give us 20 milliamps. And that is our value for IZ, the current that's flowing through that Zener diode. And then we're also interested in the voltage across that Zener diode, but that's given to us because we know that Vs is greater than Vz. So that means Vz is equal to its breakdown voltage of 3 volts. Okay, so that's how we find the Zener diode voltage and Zener diode current in that particular case. And then if we had a different case, if we had this configuration where it's hooked up part B, in that case, we just have a supply voltage that's not quite sufficient to put it into breakdown. So we've got our voltage source, Vs, which is equal to 1.5 volts, our same resistor, 300 ohms, and our Zener diode, which has a breakdown voltage of 3 volts. Okay, so it's in reverse bias, which is good because it's a Zener diode and that's how we want to have it hooked up. But then we need to check and see if our voltage source is greater than our breakdown voltage. And in this case, that is not true. So that means that our circuit is actually going to be modeled with the diode as an open switch. Okay, so if we have this diode being modeled as an open switch, that means the current has to be 0. There's no complete path for current flow through the circuit. And when we have an open switch, that means whatever voltage is applied is going to be dropped across that open switch. So VZ is equal to VS, which in this case is 1.5 volts. And these are the two quantities that we would need to find to analyze that circuit. Okay, so that is actually it for the lecture notes. Feel free to go through these. You can pause and replay the video if you need to. The lecture notes are also on Eagle, and there is also going to be a lab this week. So that's going to be posted by Tuesday, and it's going to be simulation based. So we're going to have to use LT Spice for that. I'm also looking into getting access to a breadboard simulator. I posted about that. If you were able to download it, that's great. I'm going to see if I can get a video together kind of showing how we're going to use that. I don't know that we're going to use it this week, but we will be using it in the future. So on Eagle, what I want you guys to do is obviously go through these videos, and if you got to this point, you did that, so that's good. So video, lecture, did that, that's good. There are also lecture notes, which these are for, which is what I was going through with these videos. So we've basically gone through those. What I pulled these from is another diode PDF. So that's where I got a lot of these figures from, so you can go through that if you want. It might help with some of the homework, so I would recommend at least scanning through it. There is a homework assignment based on this, and that is going to be due Sunday night, as usual, by 11:59 p.m. And there is going to be a lab posted Tuesday, and I recommend working on it as soon as you can. And I'm going to be having my office hours for related questions 12 p.m. on Wednesday. So if you're able to read through the lab ahead of time and you want to work through it, or you ran into some questions, it'd be a good time to show up, and basically we can have an online class about it on Wednesday. Okay. As always, let me know if you have questions. If you want to have a meeting like this where I can draw and talk to you at the same time, let me know. Otherwise, you can come and talk on Wednesday. All right. Good luck.